Hello students, welcome back. Let's go to section 6, General Linear Systems. Here, let us consider this system, a non-homogeneous first-order linear system, but this time we have non-constant coefficient matrix. Previously here, we used to have constant coefficient. Not anymore. So what do we do here? Well, let's forget about all those details and let's just apply the same method that we used in chapter 1, the method of integrating factor. Flip this to the other side like this, and then here is the coefficient function. So let's take the exponential of its antiderivative. So we take capital B, which is the antiderivative of A, or like this, integral. Then e to the negative b of t is going to be the integrating factor. Here, don't worry about take the indefinite integral of the matrix function. Generally, we have to convert it to the definite integral if you don't want to meddle with all those integral constants, but not this time, because we do not have integral constants to deal with anyway. This is not the final stage, it's just integrating factor stage, so we do not have plus c or plus k, so don't worry about it. Alright, now we multiply the integrating factor, this one, to each term, and that's what we have over here. The previous term here, this is n by 1 column vector. This is a square matrix n by n, and then n by 1 column vector. So multiply, we get n by 1 column vector. This 2 is n by 1 column vector. So alright, we have n by n matrix, the exponential of negative bt, times n by 1 column vector. So everything looks good, and the multiplication always has to be to the left. N by n times n by 1. Alright. And then combine these two to a single derivative, and that's by the product rule. Let's see, what's the derivative of this y? And that's a derivative, alright, nothing changes here. What's the derivative of this? Exponential stay the same, and the derivative of the inside is a. Oh, actually it's negative a, so we have negative. Looks okay. Integrate both sides. So the integral and the derivative cancel each other out. And then we plug in t and plug in t0, subtract one from the other by the fundamental theorem of calculus. And then finally solve for this y. So flip this to the other side. And oh, wait a minute, all these should be b's. Okay, sorry, okay. Same as this, except this one flipped over here. Okay, alright, so far so good. And then divide away by this e to the negative bt power. Okay, here we go, multiply by its inverse matrix, e to the positive bt power. And then combine these two exponential into a single exponential. Combine these exponential into single exponential. Looks like everything works out just great. But then again, no, however, this does not always work. What's wrong here? Can you find anything that went wrong? Big challenge. Let's go back to what we did previously. This is A. What's happening here? Antiderivative, alright, we got the integrating factor, and then multiply by the integrating factor to each term. Same deal, right? The derivative of this y is here, and then same thing here. Derivative of this is exponential stay the same. The derivative of the inside is a, actually minus a, so we have this minus. Same as right hand side. Integrate both sides. flip it to the other side. Actually, we did exactly the same thing, except that here capital A was constant. So that computation may have been a little bit easier, but otherwise looks like everything was exactly the same. But why is this not working? Anybody has an answer? The problem is right here. This transition from here to there is problematic. It doesn't always work. From here to there is problem. So this product rule here, getting there, is not working. Actually, product rule itself is okay. It's a chain rule that fails. The derivative of this becoming that fails. We'll discuss that in the next subsection. Okay, let's suppose we start from there. Why is it not working? Okay, let's look at the homogeneous solution here, and then we have to take the derivative and then get this ODE and the IC. IC will work fine. ODE is not going to work very well. How about the particular solution? The same deal. IC will work fine, but ODE will not work very well. We'll see. Let's look at the first one. Take the derivative. From here, take the derivative. Exponential stay the same. And then multiply the derivative of the inside. This is constant, so no big deal. The derivative of capital B is capital A of t. But then again, here I want capital A on the left-hand side. So this one here have to move to the left, coming here. Do you see that? This A, which I just highlighted in blue, versus this exponential I just highlighted in green, are switching places here. And this is y, so we have a times y. All works out if I can switch these two. So, if this part, exponential, and a are commutative, then no problem. But in general, they do not commute. That's why this is failing. Here's another problem here about the particular solution part. Again, the same problem here. This A here, which I just highlighted in blue, must come outside like this. Switching the order. Consequently, we get that. And from here to there, switching the order of the multiplication. It doesn't always work because matrix multiplication is not commutative. So the failure, in fact, is a commutativity issue. So if I start from this new assumption, A and B commute, then no problem. Remember, A is the original coefficient matrix and capital B is antiderivative matrix. So the antiderivative matrix and the original commute, then no problem. In general, it doesn't work. So that's the deal. If A of t, the original coefficient matrix, this one, and then B of t, which is the antiderivative matrix of A, if those two commute, then no problem. When do they commute? In general, they don't. If A is a constant matrix, then of course no problem there, because let's see, let's consider that. Yeah, okay. If is a constant matrix, if A is a constant matrix, then actually there's no problem. B of t which is the antiderivative matrix, is just A times T. So A times B of T is actually A times T, which is A squared times T. And let's see, this is equal to, let's do it this way. A T times A, yeah, let's write like this. Move T over here, and I can do that. I can switch to the order of scalar multiplication. I cannot switch the order of matrix multiplication, but I can always switch the order of scalar multiplication. So this is B times A. So yes, if A is a constant matrix, then it commutes with its antiderivative matrix. In general, it doesn't. So in what other case do we have the commutativity? And there can be many, but one very typical example is this. It's an overly simplified model, but still it's a little bit better than, a little bit more general than this. No, not that. Wrong cell. Still a little bit more general than this. Here we had constant matrix, constant coefficient, but here let us consider capital A of T is a constant matrix M times a scalar function. So this A of T has some T expression in there. So coefficient matrix here, A of T, this one may have some T expression, but for each entry, the T expression is exactly the same, so I can factor it out. So each entry has, say for example, sine of T. So take the sine of T out, and we have matrix times sine of T. That's a kind of circumstance. So the constant matrix times a scalar function, if you have something like that, then the derivative is, the antiderivative, is the same matrix, which is coefficient matrix, no change, and then this A of T becomes the antiderivative function B of T. For example, if I start from sine of T, this will be negative cosine of T basically. Then we can see that A and B commute. Well, A is M times small a, B is M times small b, and then small a, small b, these are scalars, so I can move anywhere, and then we have just M squared. B times A, again the same thing. This B and A, they're scalars, so I can move them anywhere, and then we have M squared. So they commute, they're the same. So no problem there, and then we can use the same formula that we used before, using the method of integrating factor. And you can use this directly, or because this B is M times some antiderivative function B of T, so I can rewrite B of T as M times B of T, B of T0 as M times B of T0 like this, and then factor out, you're going to get this kind of expression. Maybe too small. Increase the font. All right. Either this formula or that formula, both are kind of practical in about the same way, so no problem there. So yes, it works out if our coefficient matrix is a constant coefficient matrix times a scalar function. In that case, it works. Of course, if this is just 1, and then we have just constant matrix, well, that's what we did earlier. As for the new case, well, theoretically it works, but I didn't assign any exercise problem about this in any homework set, and I'm not about to start that. Okay, that's where I'm going to stop. We were able to extend what we did for the constant coefficient case and the method of integrating factor into slightly more complicated fashion. And then a little bit more general condition we also find that one too. If A and B commute, then that's it. Okay, that's where I'm gonna stop. And probably I'll never cover chapter 7 or section 7 here because that belongs to another course.